Hello, so this is the search and optimization prototype. So what I've got here are 3 search algorithms and 1 genetic algorithm, and I've got them benchmarked against each other. And what I'll talk about is how each of them work, what their function is, how we can apply them, and what use this can be for clients, limitations and benefits. So we can talk about a whole lot of things about these algorithms. So let's start off. So we've got this grid here, which I'm immediately going to ignore because it's very ugly and very difficult to read. I do not have the eyes for this. So what I'm going to do is I'm going to scroll down, and we are going to spoil ourselves for the results, but we've got this grid. And search and optimization, we're thinking pathways, we're thinking maps, we're thinking about evaluating trade-offs, trying to get an optimal solution, trying to find the optimal path, but also how flexible we are, how fast these algorithms are going to run. We're thinking about lots of different things here. But what I've got is a simple representation so that we can understand how these algorithms are thinking. Once again, these are not thinking, they are just trying to find the shortest paths. But you know, it's very easy to personalize them, particularly when they look so nice. No. So let's start off with the simplest one. So we have a breadth first search. So what is this? We are thinking of what is the shortest path. I think the shortest path, but instead of thinking ahead, we're just trying to explore randomly. We're just trying to explore randomly. So what happens is I lose my notes and I find them again. And so you're exploring everything step by step from the start. So breadth first search finds the shortest path by exploring evenly in all directions, layer by layer. So it's finding its way. You're starting at a point and you're exploring all nearby locations and then the ones further out and so on. You're not thinking, how far away it is. It's just the number of steps. It's quite it's narrow-minded algorithm. It's not thinking ahead. It's quite simple. It's quite stupid. So when all costs, it's good when all steps cost the same because you're just moving. But it attempts to try and guarantee the shortest path, but obviously that's not always the case. So what applications are there of this one? So breadth first search, we think about degrees of separation, social networks. So think about LinkedIn, the nodes are people, the edges are friendships, and you're trying to find the shortest connection between two people. Every connection costs the same, so it tries to find the minimum number of hops by finding the next available edge. So there are other uses, so finding the nearest available resource, so like a parking spot if you're trying to find, and also web crawling, because it'll find the next spot. But obviously, whilst those are some cool applications, there are better ways of doing this. Just trying to find the next best thing isn't forward thinking. So we've got our forward thinking algorithm now, Dijkstra's. So Dijkstra's pathfinding algorithm aims to also systematically find the shortest path, but in a different way. It's thinking, what's the shortest path? Now, I appreciate I did repeat myself there and it didn't really make sense. So what we're doing is every action that we take, we're then comparing. So let's take here when I'm at 4. God, I can't read a grid. So when we're here, this algorithm is thinking, is it shorter to go up here or is it shorter to go up here? And because it's shorter, it goes this way. So it's forward thinking. It's trying to find the quickest way from A to B, and you have that consideration. Oh, I do apologise. I just realised you couldn't see that. I was pointing here at this 04, 40, one of them, and then I was going. I was saying, is it quicker to go here or is it quicker to go here? And obviously, it's quicker to go here. So that's the thing. It's thinking about that next step. It's telling you to go down the shorter road instead of the long one. It's telling you to take the shortcut, the little alleyway through to the next road. But it's not thinking, what is the cumulative effort of this journey? It's not thinking ahead. It's not thinking, oh, it was quicker in the short term to go here, but it's slower in the long term. Because, whilst it may seem longer to get here, eventually you can get here quicker. Obviously, that's not necessarily accurate for here. I'm just trying to illustrate the point of Dijkstra's thinks about short-term gains instead of the overall trip. And that's where I move on to my next algorithm, an A-star algorithm. So an A-star algorithm is a better version of Dijkstra's. So you are constantly evaluating which direction you're going, but it's like Dijkstra's with a twist. So you've got this value called a heuristic, which is kind of like an estimate. So when I'm here, I have an estimate that this is 4 to go this way. It costs 4 steps to go here, and I think this is 2 steps. And because this is shorter, I'm going to go with the shorter one. So it's thinking about the overall journey, and it estimates what the overall journey will cost if you continue to follow down this path. So this is a more accurate, I'd say, way, because A-star, it finds the shortest path by combining the actual cost with a smart guess of the remaining distance. So, you're thinking about how far will I go overall, and this is why it's kind of the better algorithm for this use case, because if you think of Google Maps, you don't want to get stuck behind all the school traffic at 8:30 in the morning when you want to get to work. You don't want to do that, so Maps will take you the shortest path. Even if that road is quicker, it knows that there's congestion at this time, so it tries to send you to the right path. So obviously Maps can take in various other features. Google's tracking your phone, it's tracking other people's phones, and it's accumulating all that data so that it gives you an accurate prediction of when you'll get to your location. However, fundamentally, an A-star algorithm functions as a map, because you're trying to find from A to B, but it's forward thinking, what's the quickest way? What's the quickest way? How can I improve this? How can I get better? So, what else have we got? So, just in conclusion of there, I've got the breadth first, which is searching everything nearby first, kind of like ripples in a water. It's just trying to find its way. But the Dijkstra's is focused on getting the cheapest road at every step. A-star is still thinking that. It's taking the cheapest road, but it's also thinking ahead of the direction of your destination and trying to get you there and trying to estimate how cheap it will be in the future. So to make sure that you get that. So breadth first search is best for equal cost steps, where it's not going to cost more if you go in the wrong direction because it's not considering cost. Dijkstra's is good for weighted graphs because it's thinking about the cheapest one. However, A-star overall is best with pathfinding, and that's why you can see it's done the best out of all of these. So this is it explored 51 nodes, and these both explored 67. And whilst the length is the same, the fact that it explored less nodes showcases its application for this purpose. It's pathfinding. It's found from A to B the quickest path, despite the fact that I can't read a grid to save my life, apparently. So where are we moving to now? So we have a genetic algorithm. So what is this? A genetic algorithm is evolution. So we're stepping back from these search algorithms now, and we're thinking about how humans evolved. We once little fish people, and then we turned into dinosaurs, and then we turned into monkeys, and then we turned into humans as we know today. This is a horrific representation of evolution, but apologies once again, my mic thinks that I'm not talking. So what was I saying? A horrific representation of evolution, but my point is I want to get you thinking about how we move forward, how we go from A to B. So we started off very simple, and then over time we developed legs, we then started breathing, and then we started thinking, and we started using tools. This is what a genetic algorithm does. And it's that whole idea of breeding out success, but with an algorithm, and that can sound quite odd, but the way it works is you start off with a randomness. You start off and there's loads of solutions to the problem, and it finds the best two, and then it takes parts of both of those and merges them together. It breeds the It breeds the best. Survival of the fittest. The best two algorithms, the best two outcomes merge together so they can make something greater. And then what happens is, to prevent stagnation, because if you just bred the same great people over time, it would not end well. That's why it's not advised. So what you do is you add a mutation. You add this little bit of randomness so that you don't get stuck. So these algorithms, the best two are going together each time. Each time they're breeding, but then there's a slight change with them. There's a bit of randomness so that it continues to develop, because it's always going to change regardless of the best two. Because otherwise you could get into the position where the best two are coming out again and again, and then nothing changes for multiple iterations. And just because it's the best two in the random pool you've got doesn't mean it's the best overall. So the whole point of this algorithm is that it has this little bit of randomness, and it's finding the survival of the fittest and then changing the kid up a bit so that it can be tested again. And this is repeated over many, many generations until it improves. So the genetic algorithm solves problems by evolving better solutions over time using selection, combination, and random variation. So it's thinking of breeding animals. You pick the fastest horses, you breed them, and occasionally things change. And over time you get faster and faster horses before they're as fast as the speed of light, and it's amazing. So, whilst these other algorithms, these BFS, Dijkstra's and A*, they're systematically searching for the exact shortest path, a genetic algorithm guesses and improves over time. So it's not guaranteed to be perfect. And you can see that from here. The length is 20. It's performed worse than the rest of these. And as I go into the benchmarking that I've done against each of these, you'll see what this has done, but it still has its place. So just because these algorithms weren't optimal for the solutions I've given them in doesn't mean they don't have a place. And what you've got is a prototype of each of these, and then you can apply them to clients. So like I was saying, for paths with the same weight, you want BFS. For weighted graphs, you want Dijkstra's. For pathfinding, you want A*. And then for genetic algorithm, you might want those evolving solutions. So that's the thing. So, and not just that, with GA, because the number of combination that's happening is huge, there's tons of iterations that are happening, evolving solutions is often faster than brute forcing them. So that's another thing to consider. So just because this did not perform as well as the other algorithms here does not mean it does not have its place. It's still a really interesting algorithm, and it definitely has applications, and it sounds really cool. To explain to clients, it's very simple. Understanding that, you breed horses, it gets faster over time, things change, genes change, it improves, it gets better. You understand that. So I've got this benchmarking here now. So as I said, it goes over multiple iterations for these. So obviously, for genetic, it's the slowest. But despite that, it was not that slow. I will say it was still very fast. But obviously, this is a very simple solution. There's only a handful of nodes here that it's trying to find its way between. So do not take this at face value. Obviously, this can scale potentially infinitely. It can be very long. Not just that, you've got the nodes explored where A* is the best. Obviously, genetic algorithm performed worse. And then you've got the path length. Nodes weren't explored for the for the genetic algorithm because it would just completely skew it, because obviously over the course of many iterations they've explored probably hundreds of thousands of nodes. So the path length is the important value that you get out of this, where you go, it took longer. But the path length was the same, it's just A* was quicker to get there. And then also you've got this idea of convergence. So this is the idea that over 50 generations, it became the fittest. So you can see how close it gets to achieving its goal. So through that, I've given you an explanation of what each of these do. And I've explained how A*'s forward thinking and like a map. Weighted nodes are good for Dijkstra's, and breadth first is good for like connections, like LinkedIn or a social media thing where the weights are the same. So the issue is, obviously, for this, as I've explained, the genetic algorithm is not optimal. The path length found was 22 compared to the optimal 18, which obviously is 20 even, I can't read, which obviously is quite concerning. I thought it did worse than it did. So because it relies on this random initialization and mutation, and it incrementally improves solutions, it's kind of limited. So, it is optimizing, but it's thinking how close does this path get to the goal instead of thinking, is this the shortest path? Which is why it converges at this suboptimal solution where it could have been 18. But obviously there are applications. So let me get my notes. Scrolling through all the information about these algorithms. So in conclusion, what does this have? So breadth first search, it's ideal for the shortest path in unweighted environments with simple grid navigation problems and network traversal. And it works well for these because it assumes all moves have equal cost and explores in layers, guaranteeing the shortest number of steps. So real world, it's like finding your way through a maze or a puzzle. Social media with degrees of separation between users because every weight is different. And network routing where all links cost the same. So you want a simple, unweighted environment where efficiency is not a major concern. So it's kind of a simpler one. Dijkstra's is good for shortest path in weighted graphs, routing problems where cost varies, because then you want the next shortest path. It accounts for edge costs, which is why it outperforms BFS, or not even outperforms, as obviously these are the same, but it's why it's conceptually better. That's what I mean. So real-world applications can be GPS navigations for Dijkstra's and internet routing protocols, logistics and delivery optimization, and use Dijkstra's when costs are not uniform and you need optimal paths. But the A-star is ideal for real-time pathfinding, large-scale navigation problems, and games and robotics. So this is the one that you have the most application for, I think. It's the one that is very commonly used. It's known to be used for like maps and route planning, autonomous vehicles, and that just using the heuristic, using that estimate, really provides a lot of value there. And you want that when you want fast and optimal solutions, which, particularly for clients, why would they want anything else? Genetic algorithms, though, despite the fact that it did converge on a suboptimal solution, it does have purpose. The complex optimization problems, it can be really beneficial in circumstances where the problem is very large or poorly defined, because you can work through those iterations very fast, because it's trying multiple solutions and then comparing them. It's a lot faster. For these large scale problems, so you're thinking big things now. So and it works well because it doesn't require this knowledge, it doesn't require this heuristic, and it can escape the limits through randomness, and it's searching globally rather than systematically. So this can be for like scheduling, so timetables and workflow planning, engineering, design optimization, machine learning is obviously beneficial for. It's trying a lot of solutions, and route optimization with many constraints, so like things like the traveling salesman variant. So you should use the genetic algorithm when the problem is too complex, I can't speak, for exact methods, and approximate solutions are acceptable, and the search space is huge or irregular. So you want to be using these deterministic algorithms for structured environments where optimization is required, with A-star being the best overall. In conclusion, genetic algorithms are more appropriate for complex solutions, but obviously as it can be poorly defined for exhaustive methods. It's beneficial for circumstances where spaces are poorly defined, because then it's going through those exhaustive methods quite rapidly. So when you need that survival of the fittest, when you need those options, it can be very beneficial. So what can this do? So we have here 4 algorithms that clients can use. We have benchmarking, so we understand how they perform against each other. We can start to use these. We can go out and we can use this logic, add to it, and we can start applying it to these solutions that I stated. We can add it to a map. We want to help encourage a client to create a map solution. It could be for conferences, for apps to follow around conferences. You can help find the path there. You can use machine learning. You can use genetic algorithm for machine learning. So there are all these different ways of applying it. And through this talk, I've explained an overview of these 3 algorithms. So you have a fundamental understanding of how these work and how they're not as scary as they sound, and how the genetic algorithm is just that survival of the fittest, that improvement over time, and how all of these, whilst they perform the same in this circumstances, obviously knowing the limitations, where you know that A-star is thinking ahead and you know that Dijkstra is only thinking short term, and breadth first isn't thinking it much at all, and that genetic, how it can have those many iterations, how it can slow things down. You can start to consider how, for each client, what they can use it for. So overall, this gives a solid understanding. Whilst these are very limited, as these are very simple implementations for this use case, where it's only tracking around a grid, that's quite simple. This illustrates how you can use these in the wider world, and having that application and having that wide range of application, where through these 4 algorithms we have a lot going on. So that's the thing. For clients, it's beneficial that we have these in our toolkit, where we can say, I know how Dijkstra's works. I can get an A-star algorithm using. I can get that map fixed for you, and it's all about that application, how AI can help enable us to move forward, and particularly the genetic algorithm, with the AI being such a highly talked about topic at the minute. This is a really good way to get those clients interested in a way that's accessible, and particularly wide-reaching. If we can support other machine learning, if we can support gaming, these are some highly lucrative businesses, or business areas. So a lot going on there. So yeah. So thank you for listening to my explanation of these 4 algorithms.